This is Miguel Zumalacarregui from the Max Planck Institute for Gravitational Physics. Today, I'll be talking about gravitational wave lensing as a new ways to probe cosmic structure. This is work together with Giovanni Tambalo, who is a postdoc at Max Planck Institute for Gravitational Physics, Liang Dai at Berkeley, and Hoyuk Chong at Johns Hopkins University. So why study gravitational wave lensing? I would say that there are three very important reasons. So first of all, lensing of electromagnetic signals is a well-established probe of the large-scale structure and fundamental physics, such as dark matter, with very rich phenomenology. And gravitational waves is a new messenger in town, and there's a lot of new opportunities to untap. And in this sense, gravitational waves are highly complementary to electromagnetic radiation. As you know, gravitational waves are coherent and emitted at very low frequencies, and this will allow us to observe wave effects in gravitational wave lensing. Gravitational waves are also very weakly coupled, so the universe is fully transparent to them, and they're well modeled in the sense that we can accurately describe the sources, which allows us to have less uncertainty in lensing measurements, which is something we do not have for electromagnetic systems. And the third reason is that gravitational waves are detected at increasingly faster rates, which each upgrade in the detectors. So it's just a matter of time before lensed gravitational waves are a reality. So just for recap, in gravitational lensing, we think of a source in the background, which travels across or nearby some intervening object, the lens. And this lens deflects the gravitational wave. And if sufficiently well aligned or massive, this can create multiple images from the same event that are magnified and can have some time delay between them. And when we do lensing of gravitational waves, however, we need to also take into account that we're observing wave phenomena. So there's a little things that are a little different. So the quantity of interest for us is this amplification factor, F, which is a ratio of the lens to the unlensed waveform. And I'm going to be expressing this as a function of a dimensionless frequency, which is the frequency of the gravitational wave rescaled by the mass of the lens in this way. And typically, if we plot this amplification factor as a function of the dimensionless frequency, we have this type of behavior. So we have very little effect at low frequencies, and then the amplification factor starts oscillating, and then we have a behavior at high frequencies that we understand. So let's go into a little bit more detail. So I'm going to be showing in this slide waveform for a LIGO, typical LIGO source of 30 binary with 30 solar masses each companion. And here, this binary spans, so if the lens is light, so 3 solar masses, so quite light, then this source will span a certain range in this amplification factor diagram. So if in this case, the mass of the lens is very low, so we are in this perturbative regime in which lensing is very subtle. So we can see some distortions here. It's a function of the frequency, but it's a subtle effect. If the frequency goes to 0, there is no lensing, and this is we can understand this as a wave that with a wavelength longer than an obstacle along the propagation will not be perturbed by this obstacle. Now, if we go to the intermediate regime, so this would be for a lens with 300 solar masses, we're in this wave optics range in which we need to, it's really complicated. We need to solve a very complicated integral, and the results can really depend on the exact range of frequencies. So for this particular case, we have a wave that gets is modulated, and the amplitude is modulated, and then it's the amplitude is modulated, it becomes higher, then lower, then higher at the merger. But this could be very different depending on the specific case. And finally, if the frequency is quite high, we recover the picture in, we call it geometric optics, but it's the picture of standard gravitational lensing in which we receive multiple copies of the same event. And these copies will have different magnifications, and they will also be delayed from each other with a characteristic timescale. So I'm interested in seeing how we can use this information from gravitational lensing to probe the characteristic of gravitational lenses. So I'm going to be looking at a lens with a core parameterized by this characteristic radius RC, which in the limit in which RC goes to 0 is a Caspi lens, singular, known as a singular isothermal sphere, is a very typical model for a gravitational lens. And this profile is interesting because this core size can be computed and estimated in different dark matter models. For example, in ultralight or fuzzy dark matter, one can see what the core radius is as a function of the halo mass and the mass of the dark matter particle. So let's look at this, the predictions for this. So first, I'm showing this is the amplification factor as a function of frequency for in case with no core, the singular isothermal sphere. And I'm showing here logarithmic scale for very low frequencies, and then in intermediate frequencies, I'm showing the actual amplification factor, which is oscillatory, and I'm highlighting the envelope of these oscillations. And here at very high frequencies, you cannot, the oscillations get blurred into a shaded region. Now, let's increase the size of the core. So we increase the size of the core, we have some effects at low frequencies, but the main thing that we notice is that there is a modulation in the amplification factor. So there's this very rapid oscillation that gets modulated. And this modulation, as we increase the size of the cores, becomes more and more pronounced to the point that if we increase the core size enough, this modulation extends well into very high dimensionless frequencies. And in this particular case, what's happening is that we are hitting, we're making the lens so light by subtracting the core that we're pushing for the impact parameter that we have, we're pushing it into a caustic where magnifications really diverge. So this is basically the phenomenology of this model. Now, I'm interested in seeing what LISA or other detectors can do. So I'm going to be showing results of a Fisher matrix analysis. For this slide, I'm going to focus on a LISA binary with a total mass of 1 million solar masses, small core and certain impact parameter. And very importantly, I'm going to fix the SNR of the signal to 1,000. So we can compare apples to apples and forget about how far the source really is. And what you can see is that in general, you can recover the lens parameters, although there are important degeneracies between the impact parameter, the core size, and the lens mass. Now let's see what happens. So here, this is for lenses relatively light lenses, so 10 to the 5 to 10 to the 7 solar masses. 10 to the 7, it's a little hard to see, it's kind of hidden there. But now let's zoom in into heavier lenses. So heavier lenses are easier to measure accurately, but something interesting happens, which is that the contours become thinner when the mass of the lens becomes higher. Their 1D posteriors projected along the parameters, they remain more or less the same. So there's sort of a saturation that we can get in this gravitational lensing, and this is something that has been observed by similar analysis. Now let's see what happens when we vary the source mass. So this is the LISA noise curve. And this is the lens lens waveforms for different source masses. And here I'm keeping the lens mass fixed to 10 to the 7 solar masses, but I'm increasing decreasing the mass of the source. And again, we see this interplay between the frequency and the lens mass into what regime we're at, like whether we're at the perturbative regime, the wave optics regime, or even the geometric optics regime. Of course, these objects will have different SNRs. So obviously, like the 10 to the 6 solar mass binary is in the sweet spot of LISA for the redshift we've chosen. And then if we change the mass, the SNR will go lower. But this is these are all sources that could be detectable. And for simplicity, the results, I'm fixing the SNR. So keep this in mind if you want to extrapolate to actual results. So these are the projected errors for these sources in terms of the reconstructed lens mass, the impact parameter, and the size of the core. And you can see that in general, you can, if the lens is heavy enough, we can get the parameters to a precision of roughly 1 over the SNR, even a little bit better of the size of the core. Well, now, this, I want to take this to the realm of dark matter. So we can measure with a lens, strongly lensed signal by LISA, we can measure quite well the size of the core. And this is interesting because some dark matter models predict that dark matter halos form this kind of cores. And in the case of fuzzy dark matter that has all these interesting large-scale structure properties, we have some predictions for this, the size of these cores. And then we can turn this sensitivity to the core size, which I'm showing here on the right axis. So if we find a strongly lensed event, we can either detect a core, in which case, which the core may or may not be due to dark matter. But if we do not detect the core, we can immediately place some bounds on the mass of the ultralight dark matter particle. And these bounds are for LISA, if the mass of the lens is high enough, so they're sort of competitive with different bounds for this type of models. But with LIGO, because the mass of the core gets bigger for lighter halos, for LIGO, these constraints can be pretty significant. These models also predict there's a minimum mass of the dark matter halos, so we can also look at that kind of constraints, but it's unfortunately it's several orders of magnitude worse, so it's not probably not as compelling. So just to wrap up, I hope I've convinced you that gravitational wave lensing is very complementary to lensing of electromagnetic signals, thanks to wave effects, and we can prove the properties of gravitational lenses. I didn't have time to talk about this, but we've developed different methods to compute the amplification factors accurate and in a fast and accurate manner, and cross-tested against them, against each other, as well as exact solutions. This helps us recover lens parameters with significant precision and despite the strong parameter degeneracies. And hopefully at some point, we'll be able to use this not only to detect and be confident in the detection of gravitational waves, but also use that information to probe the properties of dark matter. Thank you very much. Please contact me if you have any questions.